Okay, so in the earlier video, I just sort of introduced probability to you, and we could have a range of events. We could analyze a range of things happening using different types of relationships within probability. Now, the first one I want to look at, or the one I'm going to look at for your course, is referred to as the binomial distribution. I guess the key is in the word binomial. And there are a range of others. There's one called the Poisson, there's the normal distribution, but I'm going to focus on the binomial distribution. It's quite an interesting one. Right. So what is the binomial distribution? So, I mean, a binomial distribution can be thought of simply as the probability of a success or failure in an experiment or survey that is repeated multiple times. Don't worry, we're going to break this down a little, but there's no, really just take it simply as what it is, and we'll do some examples for you to sort of see. So it's the probability, isn't it, of success or failure in an experiment. So I'm going to hit again, always try and hit the key area in terms of business and then relate it to the numbers. So it doesn't look as though we're going from numbers to business. Let's go from business to numbers. So for example, I could have a batch of items, and in this batch, I could have 1,000 items. Now I can't check 1,000 of them. I just can't. But I'm looking for defects. Right. So the question is, I'm going to say, okay, you know what? I'm going to take a sample I'm going to pick, 50 of these items to test. So this issue of repeating multiple times is me picking up, my experiment is picking up 50 items, one after the other. So I'm picking up 50 items, one after the other, looking for whether or not there is a defect. And if I find a defect, I will call it success. And if I don't find a defect, I will call it failure. It doesn't matter how you spin it around, whether you call a defect failure or a good one success, it's irrelevant. The key point is that applying it straight to business, I can only have two results, either success or failure. And we can attach some probability, if you like, to success or failure, pretty much based on past history. So, for example, or current conditions. So, for example, if I say, "Oh, is it going to rain tomorrow?" Or is it going to be summery? Well, I mean, we're in close to winter, so I know that the chances of rain and snow and whatever are much higher than failure. So so I can attack, but like I said in my earlier video, all probabilities will add up to 1. So for example, if I say it's going to rain, I could say it could be 0.7, and if it's going to be sunny, I could say it'd be 0.3. And so the same thing would apply if I'm picking a batch. If this is a good customer, and if this is a good supplier, and we know them very well, and we've never really had, say, based on previous checks, we've never really had issues, then we could say that the chance of a defect, the probability of a defect might be 5%, if you like, from this 1,000 items. Or it might be 2%, I don't know. But if it is a new supplier and we're not quite sure, or it's a particular type of product that's come from a particular part of the world, or you could have a higher probability. But the key point is, if you say the probability of a defect is 5%, that means the probability of no defects must be 95%, which is 100%, or if you like 0.05 and 0.95. The key point is that all probability adds up to 1. You with me? This is the key point. But the key point here is that what I'm doing is, yes, I will pick. Again, this is the probability. This probability of 5% is when I pick up the item the first time, right? And every individual time I pick up the item, there could be a probability that there could be a defect, or a probability that there's no defect. And so the question again, to keep it strictly to business, is to apply this. So the question is, what will I do if I notice that? I mean, I must have some kind of limit, right? I must be saying, well, if I find two items that have defects, well then I'll reject the whole sample. Maybe you might say, oh, if I find 5 items, if you like. So what you're really sort of trying to find, if you like, is a certain number of items with defects, and then you reject the items, right? Okay, so that's where we're going, and then we can now look at the maths and sort of see how can we use the idea of other simpler sort of allegories or analogies to explain how we would do this. Right, so again, I've said to you the binomial is a type of distribution that has 2 possible outcomes, right? And so people tend to look at a coin. A coin is a nice one. I mean, a coin toss has only 2 possible outcomes, heads or tails. Now, you know that a fair coin, if I throw up a fair coin, the probability of it being heads is 0.5. The probability of it being tails is 0.5. Like I said, this is a fair coin. We might have an unfair coin. We might have an unfair, when I say unfair, we might have a scenario where we actually can see that in the winter, I'm not going to have half a chance of it raining and half a chance of it being sunny. I'm quite clear that rain will have a higher probability, but both will always add to 1. Okay, great. So that's kind of the idea. You will only have, we focus on only 2 possible outcomes. Again, if I go back here, success could be that if I have less than 2 items, that is success. So 2 items or less, that's success. And anything more than 2 items within the 50 batch is failure. So again, I can structure my success and failure. I can always break up anything into 2 items, right? Greater than, less than, right? So it's not about fixed numbers per se. It's about the idea of being able to separate an idea into 2 camps, right? So this is just some numbering that I'll come to in the next video, and then we'll sort of go from there. But that's the second video. But let's just go through the letters, and then just because, don't worry. So and then you can discuss in the third video what's really going on here. So typically we use the letter N to sort of depict or say, oh well, this is the number of times the experiment is performed. And in business, this is the number of times, this is the sample. I'm going to look at 50 items, for example, or 20 items, and I'm going to pick them one after the other, right? And so we refer to that with the letter N. The second variable, P, is the probability of one specific outcome. So for example, like I said, if I pick up one item, I could have a 0.05 chance of a defect. Or, therefore, if I have a 0.05 chance of a defect, I will have a 0.95 chance of no defect, right? And so that's what the P is. The P is the probability of one specific outcome. Right, this is just a simple example. If I was to roll a die, and I was going to roll the die 20 times, the probability of rolling a 1 is 1/6, right? So if I asked you, so in this scenario, P is equal to 1/6. And N is equal to 20. I've already given you a business correlation with my defects of 50 items. Yes, I'm looking at 50 items, and then I'm looking where I know from previous history, based on previous reports and evidence, that P might be whatever 5%, which is 1/20. Right, so for the business case, your N would have been 50, and your P would have been 1/20. When you roll a die, your P is 1/6, and your N is equal to 20. I could toss a coin up several times. My P will always be a half, and N will be the number of times I toss the coin, right? I think which is the next case here. So let's just again, like I said earlier on, just to emphasize, success would be when I was rolling the die, rolling a 1, and failure would be rolling anything else, right? So rolling a 2, rolling a 3, rolling a 4, rolling a 5, rolling a 6, that would be failure. Only when I roll a 1 would be success. And those are my 2 camps, the 1 and everything else. I could do it again. I could make success the probability of having an even number. It could be 2 or 4 or 6. And therefore my probability would be a half, wouldn't it? and probability of failure would also be a half. Okay, right. Just a few other things now that I'm here. Sorry, I'll go on and give some other examples in the next video. Something else, we've already sort of agreed that the number of observations or trials are fixed. So I'm going to have some sort of n value. I'm going to say n is 50 or n is 20. I'm going to stop. I'm not just going to carry on forever. Right? And then each observational trial is independent. So for example, when I pick up the first batch, I just pick up the first batch, check it, pick up the next batch. So picking up the first batch does not affect the second batch. Picking up the second batch does not affect the third batch. Totally independent picking. Same thing when I throw a die up. I throw the die up the first time, it could be heads or tails. I throw up the die the second time, it could be heads or tails. Me throwing up the die the first time doesn't suddenly make it heavier or lighter or whatever. It doesn't, right? It's totally independent. And again, the probability of each is exactly the same. So, nothing is suddenly changed. The weather is not changing between me making these decisions, or the weighting isn't changing. So the probability is always the same from one trial to the other. Okay, right. I think I'll stop there for this second video. It's pretty long, sorry. And then I will play with some examples in the third video. Okay, thank you.